This is Unit 1, the Alphabet and Grammar of Geometry, Lesson 1.5, Brain in Hand, Problem-Solving Techniques. Please make note of both the location that you are watching the video as well as the date and time. Don't forget a parental sign-off. Make sure you turn off all distractions and that the only thing you're doing at this moment is watching the video and taking notes. Before we get started on the lesson, let's do a quick recap of graphing of lines. We're going to do this by working both with intercepts and y equals mx plus b. For intercepts, for the x-intercept, that's where y is 0 and x is something. And this, the y-intercept, is where x is 0 and y is something. The easiest way to do this, if we put 0 into the y, we just say goodbye. So we have 9x equals 15, and we can say, therefore, x equals 15 over 9, which reduces 3 goes in there 5, and 3 goes in there 3 times. 3 goes into 5, 1 with 2 left over. So 1 2/3 is the x-intercept. We go back and erase the y-intercept. If we put a 0 in the x, we cross it out. We have negative 3y equals 15. Divide both sides by negative 3. We get negative 5. That one was a simple one. Or we can change this to y equals mx plus b. I'm going to do that first. I'd like you to circle y, and your goal is to get y all by itself. We're going to do that by getting rid of x first. So our next line is going to read negative 3y equals negative 9x plus 15. Divide both sides by negative 3. And we have y equals negative 3 goes into negative 9 3 times. And that is going to be minus 5. Take a moment to catch up. So, in graphing with the intercepts, to graph the x-intercept, we're going to go 1 2/3 over and 0, so 1 2/3. That's about right there. And always label your intercepts, 1 2/3, comma 0. And then this is going to be 0, negative 5, which is right here. So I can string a line through those. Or another way we can do this is by using y equals mx plus b. We're going to start by graphing, again, our y-intercept, which is negative 5, which we already have. And our slope is going to be positive 3 over 1. That's our slope, so we know it goes up from left to right. So we go up 3, 1, 2, 3, and over 1. Or we could go down 3 this way and over 1, and you can see that we already have the correct line with our intercept. So that's how you do slope-intercept form and using the x and y intercepts. Make sure you have both versions written down, please. Talk about problem solving. Let me review really quick a very common difficulty that students seem to experience. A very common difficulty students seem to experience. So if a problem is written on the board, let's say a word problem, I've noticed this becoming increasingly common over the past few years, that students simply glance at the board and then they simply say, I don't get it. They don't try anything, they don't do anything, they don't draw. There's no interaction, just a glancing at the board, a reading just with their eyeballs, and I don't get it. It's almost like a paralysis, an inability to even start complex word problems. And I want to explain that why many of you have that kind of feeling of paralysis when you come to working with complex problems, I'm also going to give you some techniques as to how to get over that paralysis so you don't feel so stumped by complex word problems. Before I get to those actual techniques, I want to go over some new, more current scientific studies that talk about how your brain works, how our brains work, some new research. So I have 4 key thoughts for you. Now, some of these thoughts are going to seem a little strange, so they have all been footnoted, either with references to recently published books or a website article, reputable website article. You're welcome to look up these references, because some of the things I'm going to say may seem a bit strange. The first key thought is this: your fingers on your hand are directly connected to your frontal cortex. Now, some of you don't even know what the frontal cortex is. Here's the brain. I'd like you to circle, please. Use your pencil and circle the front part of your brain, or the brain, if you will, on the paper. That is the frontal cortex. The frontal cortex of your brain is basically the conscious thinking part of your brain. When you try to remember something, lyrics to a song, when you're trying to figure out a math problem, when you're trying to memorize vocabulary words for Spanish, you are engaging predominantly your frontal cortex. You're learning, you're thinking, you're comprehending. And what's interesting is that the nerve endings in your fingers directly connect, they provide information for your frontal cortex. So when I say your brain is in your hand, I mean that quite literally. The nerve endings in your fingertips send signals that empower your brain to think and process information. Again, you're welcome to check out the footnote here. Now, since that is true, your fingers are connected to your brain, there's kind of an ongoing, more recent discovery, which is actually becoming an increasing problem. Our fingers are connected to our brain, but the input we're getting from our fingers is decreasing because of technology use. In other words, it's a simple fact that technology usage is reshaping the neurological connections in our brain. For more information on exactly what is going on, I recommend the pretty short book called The iBrain, just for your information. But let me give you a scenario on why we are reshaping our brains. Now, obviously, technology is a wonderful thing. I am using technology right now to communicate this lesson with you. But studies are starting to show that our enormous use of technology is reshaping the way our brains think and perceive information. How is this happening? Well, we are keyboarding more than we physically write things out, which decreases the input of signals through our fingertips. We are clicking on mouses more than we physically color. We are tapping on screens more than we physically touch models. So we keyboard more than we write, we click more than we color, we tap more than we touch. All of that decreases the physical input that we're getting from our hands with our environment. And because of that, it is reshaping our neurological pathways in our frontal cortex. Key thought number 3. Now this is absolutely critical for you to understand, and you probably never really thought of this. Reading from a computer screen or your smartphone screen or any screen is inherently different than reading from print. And that's documented by this author, Nicholas Carr. When our eyeballs hit a computer screen or a smartphone, we have a tendency to just wander and skim. It's the way computer screens and webs are designed. When we look up something like Wikipedia, we don't actually read word for word, sentence for sentence. We just kind of jump from hyperlink to hyperlink. We skim. And that skimming is actually a skill to process a large amount of information. It's okay to skim when you're working on a computer screen. The problem is when you spend more time on a computer screen or a smartphone screen than you do in print reading, your eyeballs can get stuck in skimming mode. Therefore, when you hit more technical or detailed information, it's difficult to pick up all that information because it's very detailed. You have to slow your reading down. When we read in print, we tend to read more systematically, left to right, word by word, line by line. And when we read in print, we tend to comprehend more. Studies show that reading an article from a computer screen versus in print, people are able to recall the general theme and connection of the article better on print than they are on skimming on a computer screen. That's going to impact how I train you to read word problems in this class. Now the good news is, if we do things to increase hand and finger usage, it actually increases brain function. That is documented in the researched book by Todd Oppenheimer. So what that means is, when you do things to increase your finger usage in your study, such as writing things out by hand on paper, making drawings of information, making graphic organizers, using note cards, making note cards, highlighting on paper, making physical models. All of these physical labs, when you work in physics, all of these increase hand usage, and as you increase the input through your fingers, it actually improves your brain's ability to critically think. Let me just make a quick plug here. That is why, as a general rule, music, learning to play an instrument, actually enhances brain function because you're coordinating visual processing, reading of notes, with the movement of your fingers as well as auditory input. It's very, very healthy for improving generally overall brain function. Now, what does all of those key thoughts mean for us in this class? I'm going to be asking you and cueing you to use these techniques in class. Now, some of these you might do normally. Some of these concepts might be new to you. But the entire concept I call your brain is in your hand. And the steps to that are this. 1. When I ask you to read a problem, reading a problem does not mean looking at words on a page or on a computer screen and just glancing at it. The first step to actually reading a problem is you're going to put your finger on the paper and you're going to track with your finger on the paper, left to right, reading the problem out loud. Finger on paper. When I say finger track and read, that's what I expect you to do. Step 2, you're going to filter problems, physically filtering by highlighting or underlining keywords and phrases. Next, these 4 steps go together. You draw, label, list, cross out. Draw, label, list, cross out. Draw, label, list, cross out. Then you're going to incorporate a battery of physical techniques when you're working with diagrams in geometry. There's all about the diagrams. You're going to see these cues. You're going to trace and sweep angles, trace and mark on the diagram, trace and stretch out lines, trace and shade in regions on diagrams. You're going to use your fingers to block lengths and compare lengths. Notice all of these cues involve physically putting your pencil on the paper, tracing, and basically physically messing with the diagrams on paper. Doing that physically on paper helps your brain register the information. Then you're going to follow a process I call squeeze the sponge. What that means is that you think when you physically take a wet sponge and you want to get it dry, you squeeze it until you get every drop of water out of it. So then you can use it to wipe the counter or whatever you're going to do. In the same way, I want you to approach problems not with this question. Do not ask the question, what should I do to solve that question? I want you to check that question out. That question narrows your focus, and I don't want you to narrow your focus. Instead, I want you to look at all the problems and, in a way, squeeze out all the information you can out of the problem, whether or not you think it's related. You're going to squeeze out any information that you can by asking this question, well, what can I do? That opens up your brain thinking. Next, when you use equations, you will write your equations with two sides and an equal sign. That seems simplistic. I'm going to show you why that's important in just a moment. Then you're going to use what I call circle, plug, chug, which means when you use equations and you plug in numbers, I want you to physically circle the numbers and draw arrows and physically plug them in. That helps your eyeballs not lose track of key information. You're going to box and label your answers so you don't get lost as to what information you have found. When you deal with labels, you also should deal with units. And then last, you should check your answer. Ask yourself, does this make sense? So let's do a word problem together. Step number one, I'm just going to read the problem. You just watch, do nothing else, just listen. Mr. Farid wants to create a rectangular cement patio in his backyard along the side of his house. The length of the backyard is 4 feet longer than the width and doubled. Each bag of cement costs $6.50 and will cover about 12.5 feet squared. Perimeter of the backyard is 64 feet. Tax on the subtotal is 10%. Find the total cost of the cement backyard. What I'd like you to do right now, before anything else, after I read the problem, I simply want you to gauge, on a scale of 1 to 5, how hard do you feel this problem? When I read the problem, what was your first emotion? Was, this is easy. Or was it pretty easy, maybe average? Do you think it might be a little bit hard, or did you get that feeling, oh man, this is going to be really hard? Be honest. What's your first gut emotion when you read this problem, or when I read the problem? That's what I want. Check on that scale from 1 to 5. Do that now. Okay, now I'm going to walk you through the brain and hand techniques. Okay, step 1 is I want you to put your finger on where it says Mr. Farid, right here. I want you to put your finger there. And I want you to read aloud the problem with your finger tracking like so, left to right, every single word. Ready? Put your finger there. Do that now. Go. Read it to yourself. Finger track and read. Go. Alrighty, so now you have read the problem, finger track and read. Now the next step is do what's called filtering. You either have a highlighter on hand or use your pencil. We're going to underline all numbers as well as keywords. Filtering. It says Mr. Farid wants to create a rectangular, that tells us shape, cement patio for his backyard along the side of his house. The length of the backyard is, please underline is, it's actually the most important word in the entire paragraph, 4 feet longer than the width, then doubled. Each bag of cement costs $6.50 and will cover about 12.5 square feet. The perimeter of the backyard is, underline is again, 64 feet. The subtotal is 10%. Find the total cost of the cement backyard. Okay, so we are done with filtering. Check. Now we're going to draw a label list and cross out all at the same time. Okay, so what we have here is we know the shape is rectangular, meaning it's a rectangle. So I'm going to start by drawing that. We have a rectangle. So put over here, draw, and put over here, list. All the information, either it goes on the drawing or it goes on a list, one or the other, draw or list. So we have here a rectangular cement patio, so it's a rectangle, so draw a rectangle. Cross it out. The length of the rectangle is, which is an equal sign, 4 feet longer than is a plus concept, then the width, then double. So it's something, and then double it. So let's put this, that's going to go on our diagram. We have the length here, and we have the width. But the length is, that's an equal sign, 4 feet longer than the width, then doubled. Cross stuff out as you account for it. That's really important. That way you don't get lost. Each bag of cement costs $6.50 and covers 12.5 square feet. That's not a diagram, but that's information we need, so we're going to put it on our list. We're going to write cement, costs $6.50, and covers 12.5 feet squared. So one bag of cement is going to cover 12.5 square feet. Write that down. Cross it out. Next, the perimeter of the backyard is, that's an equal sign, 64 feet. Perimeter is a walk around concept. So I'd like you to put your pencil here, right there at that dot. Yes, actually put your pencil on the paper. Now walk around with me. Walk around. Physically trace. Put a little arrow there to represent going around. That is the concept of perimeter. Physically trace, please. We're told that the perimeter is 64 feet. So when we walked around, that whole thing is 64 feet. We have another piece of information. Tax is 10%. That's not on the diagram, so we just simply put that in the margin. Always translate percents to diagram. 10% is 0.10, excuse me, to decimals. Find the total cost. So that is your ultimate goal. So we're going to box it and put a giant question mark there. That, when you're done starting a word problem, your original paragraph should be mutilated, literally mutilated. All right, so we are done with draw, label, list, cross out. Now, we already did trace over the perimeter. If you haven't done so, do this one more time. That helps your brain register the concept of around. And now we're going to go through this process. Squeeze the sponge. Our goal is cost. So before you focus on just that word cost, look at the information you have and let's ask ourselves, what can we do? What can we write out? Okay, always start with what you can do. Let's start with the simplest thing. We're given some information about perimeter, and that's the only real number we're given is the perimeter. And before you ask yourself, what should I do with perimeter? Ask yourself this, what can I do? It's really easy to simply write out the equation for perimeter. And what is that equation? Right, perimeter equals, now walk this around with me. We have a width plus length plus width plus length. 2 widths plus 2 lengths. That's perimeter. 2 widths plus 2 lengths. So keep asking yourself, what can I do with this information? Well, let's see. Can you circle this P for perimeter? Is there anywhere else you see P? Circle it. Should have circled this, yeah, so that means it's the same thing. That means, can you then replace perimeter with that 64? The answer is yes. So I can do this. I can replace 64 equals 2 widths plus 2 lengths. Okay, problem is we still have two variables. So let's see what we know about these variables. Can you circle the W? Circle W. There's our W's. Now I'd like you to circle the length. Circle where else you see the length. So the length equals this expression. See, length to length? That means I'd like you to box this expression. Box it, please. Now draw an arrow. This is called circle, plug, chug. Draw an arrow to that L. You can replace that L with that expression. Let's see, and that gets us down to one variable, which is what we want. So we have 64 equals 2W plus 2, 4 plus W times 2. That's part of circle, plug, chug. Now we're down to one variable, so now we can solve. We can distribute this 2 to that 2, which makes it 4. So I have 64 equals 2W plus 4, parentheses, 4 plus W. Catch up. Now we're going to distribute, and when I distribute, always physically draw the distributive arrows. Please pause. Physically draw the distributive arrows. That way you don't lose a term. Let's rewrite what we have. We have 64 equals 2W plus 16, now plus 4W. Bring the 16 over to the other side, subtract it. We're going to end up with 48 equals, collect like terms. Notice when I collect like terms, you physically circle or underline the like terms. 6W, divide both sides by 6, and we get W equals 8. So W here equals 8. We put an 8 in here. 4 plus 8 is 12 times 2. That means our length is now 24. Now, a patio. Patio is not a border issue. A patio is an issue of, can you shade that for me, please? Physically shade it. It's an area concept. Let's write out the area equation and see what we can do with that. Now, if you wrote length times width for the area equation, you're wrong. Yep, you're wrong. Listen carefully. Length times width is not the equation for area. This is the equation for area. Area equals length times width. When you write equations out, I want two sides with an equal sign, always. So with that information, we can find the area of the backyard, which is going to be length. Notice I'm circling. That's part of the physical plug chug. 24, circle 24, draw an arrow. It's 24 times width, circle the W, come up and physically pick up that 8. That means circle it, draw an arrow, plug it in, times 8. 8 times 2 is 160, and 8 times 4 is 32, 160, plus 32 is 192. So the area is 192 feet squared. Now, one bag of cement covers 12.5 square feet. So we come up here, and we're going to do 192 square feet and divide by 12.5. And we need exactly 15.36 bags of cement. But the problem is you don't actually walk into Orchard Supply or Home Depot and buy 15.36 bags of cement. So we're going to be purchasing 16 bags. So now we're going to do 16 bags times our money, $6.50. 16 times $6.50 is $104. $104. plus 10% of $104 is you just move the decimal over once is going to be 10.4. So the total cost, 104 plus 10.4, is $114.40. $114.40. That, now you label, is the cost. These are the techniques I'd like you to use in solving a problem. So for this problem, I'd like you to follow these techniques and attempt to solve on your own. It'll take about 5 minutes. And then I'd like you to hit the pause button, solve this using the techniques I just showed you, turn the video back on, and check your work. Okay, let's check your work. If you've done this properly, this paragraph should be absolutely mutilated by now. There should be things highlighted, underlined, crossed out. It should look something like this. So you've already finger tracked and read it out loud. I'm assuming you did that. You put your finger on the paper, track it, read it. That helps your eyeballs pick up every detail. Next, you should have filtered. So we go here, Miss Johnson wants to plant a flower marigold border, it's a border, around her herb garden. The herb garden is rectangular, and the length of the garden is 3 times longer than the width. The area of the garden is 108 feet squared. Underline the word area. Circle the word is. It'll take 2 pots of flowers per foot to create the desired border. The flowers cost $3 per pot. How much will it cost to plant the marigold border around Miss Johnson's herb garden? Do this without tax. Okay, now that's the filter part. We draw a label list, cross out, all in one swoop here. So we are either going to put a drawing on the left. If it doesn't go on the drawing, we put it in the list. Ready? We have a rectangular garden again. So it's a rectangular garden, it's an herb garden. Cross out the word rectangular. The length of the garden is 3 times longer than the width. So is an equal sign. Length is an L. 3 times longer than. 3 times longer than. So it's 3 times longer than the width. So whatever our width is, our length is 3 times longer than the width. Cross it out. The area of the garden is 108 feet. So the area, you want to shade. Area is a concept of shading. I'd like you to physically shade that. Then draw an arrow. Now you're going to write the area equation. The area is, that's an equal sign, 108 feet squared. Cross it out. It takes 2 pots of flowers per foot to create the desired border. That's going to go on our list, not so much in our diagram. So for every foot, so make a little diagram for a foot. For every foot, I need 2 pots of flowers. For every foot in order to create this garden. Cross it out when you've accounted for it. The flowers cost $3 per pot. Again, that's not on the diagram, it's on our list. I'm going to make a little arrow here. $3 for a single pot of flowers. How much will it cost? I'm going to box that and put a giant question mark. That tells me that's my target. It ultimately is cost, not thinking about tax. Okay, so again, what can we do, not what should we do? Well, we're given information about area, so let's start with that. Area equals 108 feet squared. Can you write the area equation out? Well, sure. It's something you can do. Should you do it? Don't ask should do. If you can do it, do it. Area equals in a rectangle length times width. So you should see right now that you can substitute, which I'd like you to do. Circle this 108 and put it in area, and we have 108 equals length times width. Problem is we still have two variables here. So let's see what we can do to get down to one variable. Length, we can replace 3W with that. So it's 108 equals 3W times W. Now we're going to solve for W. That's 108 equals 3W times W is not 2W. It's W squared. To solve, we're going to divide by 3. 3 goes into 10 3 times, 1 left over. 1 and 8 is 9, so 3 goes into 18 6 times. Equals W squared. To backtrack a square, use square root. And our width equals 6. So our width is 6, and our length is 3 times 6, which is 18 feet. Now we're trying to work a border, so I'd like you to physically, if you didn't do so, trace the border. Border is not an area concept, it's a perimeter concept. So we're going to find the perimeter, like so, by adding 6 and 18, 6 and 18. 6 and 18 is 24. That's 24, so our border, our perimeter, is 48 feet. Now for every foot, I need 2 pots of flowers. So I take 48 times 2. 2 times 40 is 80. 2 times 8 is 16. 80 plus 16 is 96. I need 96 pots of flowers. So total cost, I have 96 pots times $3 each. So we're going to go 96 times 3. This is 18. Carry the 1. 3 times that's 27. Plus 1 is 28. So our total cost is $288 to buy the marigold flowers for the border. Check my work, check your work, see how close you got.